Thank you. Okay, so I took the chance of writing some formulas in the board because, I mean, I've been trying to avoid formulas so far, but today I'll have to show you some extra formulas. There's nothing I can do. So just to remind you about what we were doing yesterday, actually, now I wrote the extended kernel just to write it once, but it's not necessary to go over it. So what we discussed was this idea of Sasamoto that if you, well, I try to explain where it comes from, more or less, but the idea is the following. If you want to find the finite dimensional distributions of Taysep, and of course this is a typo, that's a T, so if you want to know, you fix, so here I extended it, so you fix m different labels, so now I'm looking at m different particles. I have my initial condition, I don't know, it looks like something like this, whatever, and then I fix particle label N1, N2, and maybe N3 or something like that, and I want to know where they are at a later time. Then what you have to do is you have to solve this bi-orthogonalization problem. So we have these functions psi, which are related to, actually they are essentially the Charlier polynomials. You shift them by the initial condition in this way, and then you're supposed to find this family of n polynomials, essentially polynomials, it's polynomials times a fixed exponential, such that this family is bi-orthogonal with the shifted Charlier polynomials. Okay, so that's what we saw yesterday. I showed you that for step initial condition, this is trivial because phi ends up being just essentially the same thing. It's just the Charlier polynomials themselves. And then if you want to do it in general, well, you need something else, right? And also for this half periodic initial condition, people knew how to do it just by doing linear algebra. But now we are in general. And the theorem, as I was saying, is if you want to do this, then you have to solve this bi-orthogonalization problem, and then the answer is going to be the Fredholm determinant on this essentially extended space, so this is just the direct sum of many L2 spaces, and this notation is meant to mean that it's L2 on the discrete interval from minus infinity to E1, and so on, but really, let's not worry about that. And then you have this extended kernel. So what I showed you yesterday was just the one-point distribution, and what you got was that, just kt of n. And whose kt of n is just this guy down here. So you solve the bi-orthogonalization problem, and then you just put it in this way. You take that information, you put it in this kernel, and you compute the Fredholm determinant, and that gives you the finite dimensional distributions. The extended kernel, which, as I've been saying, we won't use, looks like this. So if you remember what I showed you for the Ayyer process, it looked very similar. So now there's some operator, some discrete operator q, which I wrote there, raised to some power, nj minus ni, when ni is less than nj, and then plus, so this is the ij entry of this extended kernel, which is a matrix whose entries are operators, and the ij entry looks like this. So it's minus q to the nj minus ni plus that thing. Okay, so again, we won't use the extended kernel, but there it is. And this q, which appears there, which I had not written before, but we will use extensively today, is this matrix here. So think about it as an infinite matrix. Or if you want, think about it as the integral kernel of some operator q. But the integral kernel in Z2 is just a matrix, of course, and how it operates, it just operates as matrix multiplication. And it's given as follows, so if I want to compute it at xy is 1 over 2 to the x minus y times the indicator function that x is larger than y. And this is already nice, because if you may remember, or maybe not, that on the Ayyer side of things, what I had put here, it looked a bit different because I put one thing on one side and then one on the other side. It doesn't make much difference, but what we had there was a heat kernel. Here also we had a heat kernel. It was above the diagonal or below. You have a heat kernel and then plus this other thing. And this Q here, of course, it's not a heat kernel, but it's like a discrete heat kernel. Actually, that's the transition probabilities for a random walk, taking geometric 1/2 jumps to the left. So let me write that down because that's part of the key. Okay. So this is the transition probability of a geometric 1/2 random walk. Jumping to the left. Jumping left. Okay? It also turns out that that matrix, so if you remember, we had all these problems with the heat kernel not being invertible, which is, it's true, but actually this matrix is invertible. And you can compute the inverse, and it's there. It's just -1 on the diagonal, and 2's below the diagonal. Yeah, 2's below, no, 2's above the diagonal. Okay, but it's very simple. It's just, it has the diagonal with -1s, and one of the other two has 2's in there. Okay, so this is something that I'm introducing today, because we're going to use it. Let me go back here, which is where we finished yesterday. So yesterday I tried to convince you of the following thing. So I said that there were two, to try to have an idea of who these phi's may be, we needed 2 ingredients. The first one was this, and it was this idea that if you want to compute the 1-point distribution, so the simple case, or the simplest case, 1-point distribution for TASEP, just 1 particle with a general initial condition, that probability equals the probability distribution for, the multi-point distribution for TASEP with step initial condition. So somehow what you're doing, Manju yesterday asked about whether this has to do, asked me, I think later, about whether this has to do with duality. Yeah, this is like self-duality for the exclusion process. So if I start with some initial condition and I want to ask something about the final condition, and then you can sort of reverse it and say something about I start with now I put the final condition at the beginning, and then I ask what happens at the end, but now my 1-point distribution turns into the fact that when I reverse it, I get step initial condition. And this was nice. Why is this nice? Because this one I know how to solve. I just told you that the phi's are very simple when I do step initial condition. Okay, so this was the first ingredient. I should mention, actually, that this had not been used before. So the 1-point distributions for TASEP, as far as I know, nobody had written them down. But they follow very simply from this identity. So the 1-point distributions were actually known, but we hadn't noticed. Like nobody had noticed, as far as I know. That's one thing. The other thing is, as I told you, and this is what I just said, if all we wanted was the 1-point distribution, then we're done. Done, because I have the formula. I just have nothing else to do. The problem is that in this sort of scheme of things that I've been talking about, if I want to find the multi-point distribution, then I have to extend the kernel. That wouldn't even be a proof, of course. I have to prove something, but the idea would be, okay, you take the 1-point kernel, then you extend it. But I cannot extend my kernel because the kernel that appears here is this one with the right initial condition. It's already extended. I cannot try to play with that and see if I can do something. So we need something else. And this something else, so this is the second ingredient, is something, so now I finished my review from yesterday, and the second ingredient is something we call a path integral formula. And I'm going to write it right now. But the idea is that there is an alternative formula for this object, which is not a formula in terms of an extended kernel, but instead a formula instead of a single kernel. Okay, and the formula looks as follows, and then I'll tell you where it comes from. It says that the same probability that x, t, and I is larger than ai, I equals 1 to m, equals, and here I'm assuming that n1 is larger than I guess the other way around. There's a flipping here. Yeah, so n1 less than n2 less than nm. This is, of course, it's as general as you want because you just relabel the indices. And the formula looks, again, it's it's not going to look maybe very pretty. Again, it's a Fredholm determinant. So the Fredholm determinant starts like that. It starts with the same operator, KTN. Remember that, I mean, here really the only interesting thing is this. The rest is I just multiply by some matrices. Really, somehow all the necessary information is hidden here. And what this new formula does is that it sort of twists the formula around in a way in which it's even more clear that this is all that matters. So you get the determinant of I minus KT and M multiplied by the following thing. Yes. Minus Q to the N1 minus NM. And then say in a moment who this, okay, I'll say it right now. This is just the projection above A1, so it's an operator that kills everything below A1. So this is just, it's this matrix. So it's a matrix which has zeros, 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 and then at some point it has a 0, and then 1, 1, 1, and so on, where this is A1. It's just the identity where you erase all the zeros above, below A1, I guess, to the left. This is just a projection operator in L2. It's the operator in little L2 that projects on functions which have support only on this semi-integral. So you get this, and then you keep going. So N2 minus N1, psi, now I project above A2, Q, N3 minus N2, and so on. And then I get Q, N, M minus NM minus 1, psi, no, have a psi here, psi larger than AM, and I do that. Is that right? Yeah. No, there's something wrong with my formula. So I'm missing a parenthesis, that's clear. So yes, no, there should be one at the end. Because, yeah, so it's here. Otherwise it looked a bit weird. Okay, again, well, this will be important, but and I'm missing again a parenthesis. And now the determinant is being computed in all of L2 of Z, but just one Hilbert space. It's not this matrix of operators. Okay, I mean, this looks even worse maybe. But it has the advantage that it's a one-point kernel, so maybe I can try to extend it. It doesn't quite work like that. As I said, it's not like that would give you the answer, because that's not how these operations work. Really what I have to do is I have to find the phi's. That's what I have to do. I'll tell you why this helps. Let me first tell you where this comes from. So this type of formula, they were derived first for the Ayyer 2 process. And this is in the paper of Prahofer and Spohn, where they introduced this process. If I remember correctly, that's 01. Actually, this is how they derived the Ayyer 2 process. They first got this formula, an analog formula, not this one, and then they turn it into something like this, which looked better, sort of, if you come from random matrix theory. And then there's then it was realized, so this is a paper of Bordin, Corwin, and myself in 2013, that actually this way of going from something like this to something like that and backwards was much more general. So actually it holds for a very general class of processes. There's a very general class of processes essentially whenever you have a process that has finite dimensional distributions given by extended kernels like this, and there are many, many of those. Whenever you have that, you can go to a formula like that. So what one has to do to prove this is sort of see that this kernel here satisfies all the necessary hypotheses, and you can check on the paper. Actually, it doesn't satisfy all the necessary hypotheses, but then you tweak a little bit the proof, and it gives you this. So I won't say more about that, but this is something that had become clear for the last, I don't know, 5 years or a bit more, that these type of formulas were useful for getting other properties of this process. Now, why is this useful in our situation? Look at what's happening there. So this is just, forget about this one, because this is sort of n1 minus nm is negative. But this is the transition probability from time n1 to time n2 of my random walk. This is the transition probability from time n2 to time n3 of my random walk, and so on. So really what I'm looking at is I have a random walk going from time n1 to time nm, and I'm asking it to stay above a1 at time n1, a2 at time n2, and so on. So this is just a hitting probability for my random walk. So this red thing, again, this red thing, this equals the transition, the probability for the geometric random walk to go from time n1 to nm, not hitting the hypograph, because I have to stay above. And for some reason I had thought it was the epigraph. Let me make sure that I didn't make a mistake. Yeah, well, anyway, not hitting the hypograph of this curve. So at time n1, I have a1, at time n2, I have a2, and then at time nm, I have am. And so the hypograph that I'm looking at is really this. Right? And then on the other times, I can do whatever I want. Right? I just do this transition. Okay. So is this clear? So, okay, this already tells you something. It tells you that somehow this hitting probability is showing up naturally in the problem. And this is why it's going to appear in the limit. As I said, it doesn't really give you the answer already, because this is just sort of ideas, but you have to work a little bit to try to turn it into a guess. But now essentially you know that the answer has to have to do with hitting probabilities of a certain random walk, somehow. And then you have to work a bit to produce a guess, but I'm going to tell you what the guess is. So essentially these phi's are not going to correspond, are a bit more complicated. They will correspond essentially to the probability that you hit that curve at a certain time. And then this sum is going to essentially correspond to the, if I want to hit the probability, then I have to hit at some point, either at k equals 1 or k equals 2 or k equals 3, and that's this sum here. So that's going to be the idea. Now the actual solution is not going to be written directly in terms of hitting times, but instead I'm going to think of this as solving a certain heat equation. This is like, you can also think of this as the solution of a heat equation, a discrete heat equation, where the Laplacian is replaced by this Q, and you have a boundary condition of 0 at the curve. It's the same thing. So here I'm going from time n1 to time nm with 0 boundary conditions on these points. And if I try to solve that, it's going to be given by exactly by that. So that's the key idea. So So we use this to guess, and I just told you more or less where the guess comes from, and leads to the following. Okay. As I said, in this lecture, I have to write formulas. There's nothing I can do. So write psi of k as e to the minus t over 2, that's just a number, and then e to the minus t over 2 grad minus, this is just a discrete backwards difference operator applied to q to the minus k. So here, so this is just the generator. If you think about what this is in terms of Markov process theory, this is just the generator of a Poisson walk going to the left. This is the generator of a Poisson walk. And the reason why it appears here for TASEP is that every particle, if you run TASEP with just one particle, then it's just a simple Poisson random walk. Essentially, that's why this is here. And whose grad minus, so grad minus of f of x equals f of x minus f of x minus 1. I'm going to use later grad plus of f, which is of course the same thing, but now like that. Okay, so I say write this thing as that. That's just, this is an identity, and one can check. It's not hard. This is really, if you know orthogonal polynomials, this is essentially this is the Charlier weight, and this is a difference operator. So all you're doing is you're applying the usual discrete difference relation for the Charlier polynomials, and you do it recursively, and you get to this. So this is, or you go to a classical book on discrete orthogonal polynomials, or you go to Wikipedia or something like that, and you find something like this, and then you rewrite it in this form. That's convenient for us. Okay, so I'm going to write it like this, just because it's going to be easier to compare with what happens now. And now I'm going to let h and k be the solution of the following problem, of this sort of heat equation that I was talking about. Let me say here, n and n are fixed. So fixed 0 less than k less than n. Okay, and the problem is the following. So it's just very unfortunate, but it's not going to be a heat equation. It's going to be a backwards heat equation. I have to, this is just for technical reasons, I have to solve it in that direction, not in this direction, but it doesn't make any difference. So think of this as the inverse of the heat kernel. It's a discrete heat kernel. Okay, applied to h, n, k, l, z. And what this should give me is h, n, k, l plus 1 of z. And this is for all L less than K. So this is sort of the heat equation part. So I hit I hit my function at time L with this Q star inverse, and I get the solution at time L plus 1. So that's the first condition. The second condition is an initial condition. Remember, these are fixed, so at time K, this should be 2 to the x0, sorry, yeah. So it should be 2 to the z minus the initial condition. And finally, I have to put the boundary condition, and the boundary condition is the following: h n k of L at the boundary, which is given by my initial condition. This should be 0 for all L less than K. Okay, so I am solving this sort of backwards heat equation, discrete heat equation, with some given initial condition, and with this zero boundary condition on the curve given by the initial condition of TASEP. But now I completely forgot about TASEP. You just give me these numbers and I try to solve this. Was a question? Okay. So suppose I can do that. Then phi n k equals e to the t times e to the t over 2 grad minus adjoint. So it's just like here. Oh, I made a mistake here. So this is a function of one variable. This is a function of two variables. So this identity didn't really make sense. So the identity really is this. Either, so I just have to get this one. Yeah, it's the other way around. X 0 n minus k comma z. Yeah, you remember the size. Sorry. Hope it's this is what I meant. It's not the most compact way of writing it, but that's what I meant. So, because that's the function that really appears inside the kernel. Okay, so now, just as I wrote here, e to the minus t over 2, e to the minus t over 2 grad minus, I write the same thing, and now this is going to be applied to my solution. And those are the bi-orthogonal functions. So what you do is, you solve this backwards heat equation with these conditions, and then you multiply, you operate with this sort of Poisson walk on it, and that gives you the phi. Now you put it inside, and you have the solution, then you have to do something, of course. Is what I'm saying clear? You solve the equation, I'm going to prove it. Okay? So maybe all that you need to understand for now is that this function, which is the function that comes from Sasamoto's theorem, if you want, has this representation that's sort of straightforward. And then I'm just claiming that there's a certain problem, and if I solve the problem, and I take my solution, and I compose it with this guy here, I get exactly the bi-orthogonal function. Let me show the proof. It's really easy. So first, okay, so one thing that one has to do is check that there are solutions and that the solutions are unique. But that's actually simple because the initial condition one can check lies on the kernel of this matrix. So if I apply Q to the initial condition, to 2 to the Z, that gives me 0. Actually, Q star to Z, it gives to 2 to the Z, it gives me 0. So you can sort of start working your way backwards. So I'll just say existence plus uniqueness is actually easy. Okay, so we at least we have existence and uniqueness of that. So I have to check that 2 to the minus Z H K N of Z is a polynomial of the right degree. That's also easy, actually. If you check, for instance, this one is a polynomial, when I compose by 2 to the minus Z, it's a polynomial of degree 0, it's a constant. And then when I start applying, then I take this and I start applying that operator to get the earlier conditions. Oops, I'm sorry, I'm making many, there's more formulas here, so it's hard to get them all straight. Again, there's a typo here, but it should be a posteriori an obvious typo because this is a function of two variables, this is a function of one variable. So I have to tell you something here. This is a times 0. Okay, so you have to look at the solution. This is the backwards heat equation, and then I have to look at it times 0. So essentially what I do is I start with this polynomial of degree 0 after I take the 2 to the Z, and then I operate with this recursively, and every time I do, I increase the degree of the polynomial by 1, but I can check it. So this is easy by induction. Okay, so now let's check the bi-orthogonal property. This is the important part, of course. I'll do it on the other side. What do I have to do? Well, I have to compute this, right? So I have to compute the sum. Actually, let's recycle the board. So this thing, it equals, this equals sum over the integers. So my psi k, I wrote it in this other way, so I'll write it as e to the minus t over 2 grad minus q to the minus k x0 n minus k comma z. And I did not write the e to the minus t over 2 because it's going to cancel with the e to the t over 2 on the other side. So that's no mystery there. And then this should be multiplied by e to the t over 2 grad minus star h k n 0 z. That's what I'm postulating. This thing should be 1 if and only if, and of course this k here is an L. 1 if and only if k equals L. That's what I have to show. Now this thing is really, I mean, maybe you already said it, but there's another way to do it. This is really the inner product of e to the minus t over 2 grad minus q to the minus k x0 n minus k dot. So it's the inner product of that function with this function, e to the t over 2 grad minus star h l n 0. Actually, this step is not really needed, but the point is that I have this e to the t over 2 grad minus star, so I can put it on the other side. I just bring it to the other side of the inner product because it's the adjoint, and it cancels this one. I didn't show you that this is invertible, but actually it is, so this makes complete sense. So this and that, they just go away. That's the reason why I put the e to the t over 2 grad minus star on the solution. Okay, so now I'm going to write this thing. This is, so now it's this hitting against that. So this is just the sum. Actually, let's not even write the sum. So this is q to the minus k applied to h, l, n, 0 evaluated at x0 and minus k. That's what it is. You work out the sum. That's exactly what this is doing. So I have my operator acting on this function, and the function here, I mean, 0 is fixed. So I apply it, and then I see the solution at position x0 and minus k. That's how these things operate. Okay, that's good. And now I'm almost done. So now I have there's two cases. So first, if I haven't yet even used the problem. Now I'm going to use this problem that the h's are solving. So if, let's see, so if k is less than L, then, so if k is less than or equal to A, then this thing equals, so look, what this problem is doing is that when I operate with Q star inverse, yeah, and I am missing a star there, I have to put the star, but when I operate with Q star inverse, I increase this index by 1. That's what this solution is doing, okay? So, no, what am I doing? It's not here. And then it's going to be 0 by the boundary condition. Yeah, I'm just trying to, this is q star to the minus k. So I apply these k times, and this is going to be h l n of k comma x0 n minus k. And this is 0 when k is less than L. That's what the boundary condition says. I flipped L and k. But it says this is 0 if you evaluate exactly at the boundary at the right time, if L is less than k. So if this index is less than that one. And that's exactly what is written here. If k is less than L, then this is 0. I'm going to write the answer because, of course, it has to be this. So when k is less than L, this is 0 because of the boundary condition. When k equals L, this is 1 because of the initial condition. The initial condition says hk k of z equals 2 to the z minus x0 of n minus k, and that's exactly what I have here. So I'm going to get 2 to the x0 n minus k minus x0 n minus k. That's 1. Okay, so I got it at least for k less than L, and for k larger than L, it's very similar. While if k is larger than L, okay, the problem is that if k is larger than L, I get to k here, and then I cannot keep going because the problem stops. I have only solved it up to time 0. So, well, I do what I can with it. So I have q star to the, okay, so I had minus k, but I can only apply it L times. So I'm going to be left with minus k minus L. So this is the number of times I could not apply it. And then I get h n L 0, not 0, L x0 n minus k. But I told you, so this equals 2 to the z minus minus k. That's, again, that's the initial condition. And it turns out, and 2 to the z, this function is in the kernel, you can check it, of q star minus. If you apply q star minus to the function 2 to the z, this is just a constant, you get 0. I already erased the definition, but it's completely clear. You have 1s here, 2s there, one with a plus, the other one with a minus, so you just get it straight away. So that's 0 if L is less than k. And that's essentially the end of the story. End of the proof, not of the whole story. So if L is less than k, then again you get that this is 0. Questions? So in the end, when one sees what the solution is supposed to be, the proof is easy. It's not that, okay, I'm not exactly sure how to answer that. It's not that it is important. It's just part of the bi-orthogonalization problem. So the bi-orthogonalization problem comes from, you ask for these to be polynomials. If you want to know why they have to be polynomials, you have to look at the proof. But essentially, this bi-orthogonalization, so the point is that these ones are essentially polynomials. And then when you apply the Ayyer meta theorem, you get a certain matrix which has to be inverted. And what this does, this is just a change of basis. So that if you want to invert a matrix, you can change basis so that the inverse of the matrix becomes the identity. And what this is asking you to do is to find the change of basis. That's really all that's going on. But the basis in which you have to look at things, so on one side you have the polynomials because that's what you're given, so you have to sort of exit with polynomials on the other side. It's just, essentially it comes from the linear algebra problem that's being solved. So it's fundamental in that sense. If you had a different problem where these are not polynomials, then so there are problems where what you look for here is something slightly more complicated, and there's more general versions of this. But usually you can just think that they're going to be polynomials. Okay, good. Okay, so this is nice because we have these bi-orthogonal functions, and so this gives me a proof, and this theorem now holds. But if you want, the flip side is that now I have this description in terms of backwards heat, kernels, whatever, and that's not, I mean, I lost the picture of these random walks, which we liked very much. But actually, if you remember from sort of a course on Markov chains, you can always, this is not really the classical case, but you can, if you want to compute the probability that a random walk is going to hit a certain curve, that's given, if you want to compute the distribution of the heating time of a random walk, that's related with an equation of this form. Okay? It's like a standard textbook exercise in Markov chains. This is not exactly the same, but you can check. It's essentially the same. You can check that these guys are given, so let me say it here. So then one checks that H, N, K, 0, Z is related to a heating time problem. Okay, it's almost a bit stupid what I'm saying because that's where it comes from, but you can check exactly what it is, and I don't want to do a calculation because I won't have time. So it's related to a heating time problem for the random walk. The thing that I want to say, this is for all Z less than n minus k. So this is telling me if I start below the curve, then what I'm computing here is the probability that I hit the curve exactly at time k. For us, you have to get the indices right and all that. You can see it on the notes. But that's if I start below the curve. If I start above the curve, then, okay, it doesn't really mean anything in terms of the random walk. This is like the method of images, if you want. So you're doing something below the curve, and then there's some sort of extension above. You can even see it here. If Z is less than x0 n minus k, then this is giving you a probability distribution. Above, this thing is growing, and it won't give you anything. Okay, but we worry about what happens below. So really, the way to write it, the simple way to write it, and this is, again, not a big deal. It's just rewriting things. So after some work, if you want, after some work, but not anything special, and you can see it in the notes, what you get is the following. One gets the following thing. One gets that kt of n can be written as follows. It can be written as e to the minus t2 grad minus. So I'm just writing, essentially, I'm first writing the psi's, and then I'm going to write the phi. So e to the minus t2 over 2 grad minus q to the minus n, and then a certain operator g0n, and then e to the t over 2 grad minus. Okay, so this is, for now I haven't done anything. I just rewrote it in a certain way, and I have to tell you who's this guy. That's the point. Where G0 Z1 Z2, so that's the new operator, equals the probability for a certain random walk which starts at Z1 at time 0, and the probability that the following thing happens: first, that it hits the curve before time n minus 1, and second, that at time n minus 1, it ends up at Z2. At time, and yeah, I have to tell you what curve. Yes? So I have to tell you who are these guys. So this Z, this is a random walk. Let me write it like this, which has transition probabilities Q. So it's just a geometric random walk. And tau, this is the heating time of this region. I guess it's easier to write it, to just draw it. So I have, they decrease, x0 of 1, x0 of 2, up to x0 of n. So this is time 0, this is time n minus 1. And what you want to hit is this, the region just above. So really the epigraph of that curve. Because this random walk is given long steps. Actually, it's going down, so it ends up not being very important. But you could hit at the curve, or you could hit right above the curve, or much above. Okay? So it's like in the continuum version, but you want to hit the epigraph. But actually, this is a misleading picture, because there's nothing here. So it's the probability that I'm going to be right above this point at time 0, or right above that point at time n2. Yeah, like this. Yeah, that's that. Okay, let's really not worry about the details. But if you have a question, Mateo. Okay, it's a similar thing as what we have in the limit, but for this random walk. So I run this random walk, and I start asking what the random walk can do. So the random walk is going to, actually no, I made it more misleading myself. But this is really completely filled in this case. And I just walk, and I see when I hit the epigraph. And I ask, what's the probability, number one, that I'm going to hit before time n minus 1, and then that I exit at some specific point. This really just comes from this formula, then you sum this thing, and you reinterpret it in the right way and check something, okay? But the main point here, I haven't finished, because I told you that this interpretation in terms of random walks holds. This is whenever Z2 is less than x0 of n. Because I'm computing this heating time problem, and that makes sense if I start or I end below the curve. If I start or end above the curve, then of course this is completely trivial. So really what I get is this, but only below the curve. Okay? Okay, so by now I guess several of you may be lost because there's sort of computations here, but in a way this is a long road to get to saying that, if you remember, I erased it. What was written here, this path integral formula had to do with a random walk not hitting a certain line, or hitting the line. It's exactly what's written here. It's a way to recover that, except that in this version, it only works below the curve. So now you have to say, okay, what do I do if I want to go above the curve? Because I would like to have a formula which works for all Z2, not just for Z2 below the curve. I am trying, so just to sort of to put it in perspective, what I'm trying to do is to write this kernel in terms of my random walk hitting probability in such a way that then I can take limits and I expect to get a limiting operator in terms of my Brownian motion hitting probabilities when I rescale. So this is nicely given by my random walk hitting probability below the curve. Okay, but actually this is not hard. Because you can imagine that if these phi's were polynomials, and they are polynomials, well, they are 2 to the z times polynomials, then when I start adding them, as I do in the formula, I already erased it, but remember that the formula is sum from k equals 0 to n minus 1 of the psi's times the phi's. If I add the phi's, I will still have polynomials. Sum of polynomials are polynomials. So let's say, but from the bi-orthogonalization problem, so from start, one checks that 2 to the minus z2, g0, n, z1, z2 has to be a polynomial. And I can check that even though this formula only works for z2 less than x below the curve, it is actually satisfying the same thing. So if I multiply by 2 to the minus z2, this thing is a polynomial. It has to be. It has to be because, well, I'm saying it here that it has to be, but you can also check it if you want. So what do I do now? Well, I just extend analytically. I have a polynomial, and I know it for infinitely many points. There's a unique polynomial that extends it. Right? There's only one polynomial that can coincide with this one for all z2. That's not very useful. I mean, that's true, and I can write it down, but it's not very useful because it's not explicit. And remember, I want explicit formulas because I want to take limits. But actually, it's very easy to extend this explicitly. So I'll show you how. Okay, and so we have, well, I'll write this as G0n, Z1, Z2. Okay, I can write it as follows. I can write it as the expectation starting from the same point of, okay, so if how does this work? I'm gonna make a bad picture because this random walk actually goes down, but let's forget about that for a moment. If I want to do what this event is asking me, I have to do something. I have to hit at some point, at some time tau, and then from this point on, I'm free. I just keep going, and I have to ask it to end at, let's say, z2. So the way to write that down is the following. This is the expectation of q to the n minus 1. An n minus 1 there, sorry. So it's q to the n minus 1, starting from wherever I hit a time tau, so I start from there, and then I have, it's not n minus 1, it's n minus 1 minus tau of whatever it is that I hit, and then I go to z2 times the indicator function that I hit before n minus 1. So if I want to hit, I have to hit before time n minus 1, and then from wherever I hit, in the time that I have left, I have to go to z2. This is just a straightforward decomposition. Is that clear? If I want to ask for the probability that my random walk starts at z1, ends at z2, and hits this region, that's the same as computing the expectation of, well, first this indicator function. This indicator function is just this, so I haven't changed anything yet. But if I want to get to z2, what I have to do is, well, I will have hit at some point, and then from that point on, I already hit. So the rest is free. And then I just do the random walk, and this is exactly the transition probability of that random walk. And the nice thing is the following. So the nice thing is that this operator now can be easily extended. So now you see, all the dependence on Z2 is inside this term. That's the only thing that depends on Z2. So if I want to extend this to a polynomial in all Z, all the integers, I only have to extend this to a polynomials in all the integers. Really 2 to the minus Z2 has to be a polynomial in all the integers. And that's not hard. I mean, you can just write it down. Okay? So let Q, so this is the notation in the notes, Q bar n Z1, Z2 be the, let's say, the analytic extension of Q to the n to Z2. Okay, so Q to the n is the transition probability of this random walk. So this random walk is going down. It takes geometric steps down. So the support of this measure, it has to be, it can never jump. It has to at least jump by n steps below, and then below it can be anything. But above it's always going to be 0. You can write it explicitly, and there's a simple formula to extend this to all of Z2. And if you do all this, you get the following theorem. So the theorem says the following. It says that K Tn, so the kernel that I'm looking for this whole time, equals I'm going to write it as this. So it equals, okay, I'm going to use the notation in the notes, and then it's just the product of two operators where S minus T minus N equals, this is the easy part. It's the part that doesn't have to do with G0N. So this is just E to the minus T over 2 grad minus Q to the minus N star. It's the first part in that decomposition on the top. And S bar minus T comma N of Z1 comma Z2 equals the following thing. So it equals the expectation. It's what I wrote there, but now with the extended Q bar. So now I'm going to have E to the T over 2 grad minus. It comes inside. Actually, let me not write it like that. So what I should write is Q to the Q bar N minus tau composed with E to the T over 2 grad minus. And at Z of tau, comma Z2, indicate a function that tau is less than N minus 1. So it's a certain functional of my random walk. It's the expectation of a certain function of my random walk depending on the heating time of the curve, where the curve is given to me in terms of the initial condition. So if I may, really, I'm going to take, I don't know, 4 more minutes than I should. And this is the answer. So if you want to compute, I'm throwing some things under the rug, or really many things, but if you want to compute the the probability for your for TASEP, what you have to compute is the Fredholm determinant of this operator, and this operator is. So let me leave that for later, because I want to do an example, and then I'm going to tell you how you do the scaling limit formally, and why we get what we would want to get. But let me do an example, just because this looks, up to a point, it looks horrible, but it should become good at least for step initial condition. That's sort of, in a way, that has been it's the guiding principle of all this. The step initial condition is the easy one. I use it to try to build other things. And so this one should be good for the step initial condition. So let's see, step. Can I say anything about the step initial condition? So again, step initial condition is this. So particle 1 at -1, particle 2 at -2, and so on. So what I have, so the picture is the following. So notice that all I have to do is compute tau. I need to compute, if I can characterize this heating time, well, I just put it in and I keep going. So this is how this looks. So bad picture again. Over here. So at time 0, I'm at -1, then -2, -3, and so on. Okay? -2, -3. Now, remember the definition of my walk. So my walk was like this. So my walk, it takes geometric steps, but they're all strictly down, or strictly to the left. And I want to hit this region. So it's very easy to see, it's completely straightforward, that if I start below, there's no chance that I will hit. Because at every step, at least I give one step down, and then one step down, and one step down, and one step down. There's just no way. The only way in which I can hit is if I start on this epigraph. It's sort of what happened for step initial condition in the KPZ fixed point, if you remember. That you had to go below, and there was only one point where you could go below in the center. Okay? So here, tau equals, tau is 0 if x0, sorry, if the starting point is above 0, and infinity otherwise. And this means, I won't write it, but this means that when you write this, tau, essentially, you get this projection. So if z1 starts below, then this is 0. If z1 starts above, then tau equals 0. You hit exactly at time 0, so this whole thing really simplifies because there's no tau here, and this becomes the starting point, and this is, of course, 1. So you get a very simple formula. And you check, and this is the same formula that had been derived earlier. Okay, so that's at least the simple example. Okay, if you want to do this for the half periodic initial condition, it's more complicated because now it's going to look like this. So now instead of going by 1, I go by 2. So there's always a chance I could hit, and you have to compute the distribution of that tau. And it's more complicated, but you can do it, and you also recover the same formulas. Now, where should I? Okay. I'm going to erase here, because I want to very quickly explain where the scaling limit comes from, without much detail. And then I'll stop. So it's sort of comforting that one can do this, at least for the simple initial condition, and get something explicit. For half periodic initial condition, it can also be done, and you get something explicit, and you can take a limit. But the whole point of this idea is that you won't have to compute the tau explicitly. Because if you give me a general curve, I can't say much about tau. The point is to take a limit just directly. And the way to do it is, essentially, one realizes that Q inverse, okay, maybe I shouldn't try to take too much time, but the point is the following. The point is that Q, if I compute Q to the n, that's the transition probability of a random walk. And when you try to take the scaling limit, of course, you have to work out the scaling, and when you work out the scaling, this operator here is going to get scaled, and it's not too hard to believe that it's going to get scaled in the right way, so that by Donskir's theorem, this is going to converge to a heat kernel. It's just the transition probability of a random walk. It's a simple geometric random walk. You subtract the mean, and you rescale, and it's going to go to the heat kernel. So that's one thing. So whenever we have essentially this part here, n minus tau here is positive, so this is going to go to a transition probability of a Brownian motion. So that's one thing. And then the other trick is the following, is that one notices that Q inverse is actually the identity plus 2 times this grad plus. I'm doing things very formally. So you write, so let's look at this, because somewhere I should get my third derivative. I won't show you where, but I'll show you the idea. So one writes S minus T minus, or N, you write it as e to the minus T over 2 grad minus plus, and I'm being, plus N times the log. And this, what I'm writing here is extremely formal. So it's not to be taken seriously. But I write it like that, right? I have e to the minus T over 2 grad minus, which is this. And then, I guess I'm writing the adjoint. And then the q to the minus n, since q inverse is this, then I can write q to the minus n as e to the log of q to the minus n. And I bring the n here, and I get this expression. And now what you do, this is not the real proof, but this is a way to see it. You expand this in Taylor series after rescaling, so there's going to be many epsilons around, and the first order is going to be an epsilon to the minus 3 over 2 coming from here. There's going to be, this n is also going to contain this epsilon to the minus 3 over 2. So you expand this in Taylor series, and you get something like, if I remember correctly, it's something like this. You get like minus grad minus plus grad plus, and then I think you get the second derivative, which I'm going to write like that, and then something like this, the third derivative, and then plus other things. Everything scaled with epsilons and so on. So then you rescale the lattice in the way that has to be rescaled, and you work out what this is. And it turns out that when you put it all together, what you're left with is something that's going to look like 1/3 the third derivative. Okay? But this is just, you think of doing, so this would be f of x minus f of x minus 1, but it's not going to be minus 1, it's going to be minus epsilon and a half after rescaling. So this is this, then plus f of x plus epsilon and a half minus f of x. So that's the first one, that's the second one, then this is the second discrete derivative and so on. You expand in Taylor series in epsilon, and everything cancels. At the zeroth, first, and second order, they all cancel. You're left with nothing. And the first non-trivial term you get is the cubic term in epsilon to the half. That's the epsilon to the 3 halves. And that looks exactly, when you check it, it's just the third derivative operator. So then you have to, okay, work out the details, take a limit, but that's how the third derivative appears. And of course, as I was saying, the q to the n is going to a heat kernel, so these random walks are going to Brownian motions, and so this random walk heating problem is going to a Brownian motion heating problem. And when you take the limit, you get what you want, which is this thing that's going to start to look as a scattering operator, as the Brownian scattering operator. Okay? There's many steps afterwards, and this convergence, of course, it's not proved like this, but that's the main idea. Okay, so thank you for holding till the end, and that's it.